In this video, we're going to take those relationships we saw between the different variables that describe the behavior of a gas, and we're going to try to build them into equations that we can actually use to make predictions. So here I have this table that's filled with what we call our simple gas laws. And there's lots of them. It's like a lot of old scientists at the turn of the century that were studying gases. We have Boyle's law, Charles' law, Gaelusik's law, and Avogadro's law. And all of these are describing what we saw in those demonstrations. So what we saw when we were looking at the syringe with the balloon in it was that relationship between volume and pressure. And we saw that pressure was proportional to the inverse of volume. So that way, if I increase pressure, volume would decrease. Well, we can translate that relationship into an equation that describes pressure and volume before and after a change, which we're going to call P1V1 and P2V2. The idea is that if they're proportional, then the product of my pressure and my volume will be equal to the same product of my pressure and volume after I made some change. So if pressure goes up, volume must go down for those that product of those two values to be the same afterwards. Which is to say, we can convert this relationship we observed that pressure and volume are inversely proportional to one another and create a law that describes a system before and after a change to either pressure or volume, which we have right here. And we have the requirement that pressure and volume's product will be equal to its product after a change if temperature stays constant. And so remember when we looked at that, the temperature of the room didn't change. We didn't put it in ice, we didn't heat the system up, anything like that. We then saw in our practice problem with Charles' law that temperature oops, was proportional to volume. And that relationship can then be described in that same before and after equality, where we take our system of temperature and volume, that if temperature increases, volume will increase. And if we divide our volume by our temperature, that'll be equal to the volume and temperature divided by one another after the change in temperature or in volume has gone into effect. And so that proportional relationship is going to translate into this relationship here between volume and temperature that we consider Charles' law. And again, this only works when we have our pressure constant. So it must be done at atmospheric pressure, which we can do with balloons. Things that can expand volume will allow a gas to stay at a constant pressure. Next, we looked at the effect of temperature and pressure. And when we did this, it was with a egg in a flask and looking at the pressure inside the flask of the gas decrease and increase with temperature. And we saw that temperature was proportional to pressure, similar to temperature being proportional to volume. And so here we can build in another equality. This is Gaelusik's law. It's another simple gas law looking at just the relationship between pressure and temperature when we hold volume constant, so in a rigid container. And what we found is a similar relationship that we see between temperature and volume. And we can set it up in this kind of before after equality. Now, we also looked at the generation of carbon dioxide gas, and this brings us to Avogadro's law. What we learned is that our number of moles is proportional to our volume. That when we increase the moles of a gas, we increase the volume of it. And that is, in essence, Avogadro's law. And so that requires keeping temperature and pressure constant. But we also noticed in our own demonstration that we looked at that the number of moles was also proportional to pressure, that if you could keep that volume constant, the pressure would increase and build in the system. And so we get this equality here related to volume, but we could create a similar one, which was not Avogadro's law, but is very similar, of pressure over number of moles would be equal to the second pressure over the second number of moles as you increased or decreased it. And so we have all of these relationships that can be expressed in equations now in this kind of before and after scenario. And we have this helpful kind of way of representing most of these in our combined gas law. Our combined gas law is taking Boyle's law, Charles' law, and Gaelusik's law that shows the relationship between pressure, volume, and temperature, and puts those into an equation that allows us to make a prediction if a change to a system occurs. So we have our pressure, volume, and temperature equations combined from these three laws to build this one right here, that the initial pressure, volume, and temperature will be related to the final pressure, volume, and temperature if a change is made, like temperature changes, volume changes, or pressure changes. And so we can predict what happens if we make a change, or we can predict the way something was after a change occurred, any of these variables. And so we can use this if we have a problem that's asking us to determine what volume, pressure, or temperature is after some sort of change happens and we know our initial quantities. Then we can use the combined gas law. You could also use any one of these simple gas laws as well, but it's always nice to just remember one instead of four or three. um, so looking then at all four of these together, we get, because chemists love to compress information. It's one of our favorite things. We can actually take all of these laws that were developed and bring them together into one equation. When we bring all of these relationships together, we can describe it as the number of moles being proportional to pressure, volume over temperature. So kind of taking Avogadro's law and applying it to our combined gas law. If we wanted to make this an equality, we could create a before and after sort of equation like we have for the combined gas law. But what we find is more useful and is pretty interesting here is by taking these four variables and their relationships and representing them on one side of an equation. And when you do that, and if you take a gas in different situations, maybe different temperatures, volumes, pressures, you find that this product of the pressure and volume divided by the temperature and the number of moles will produce a consistent value. And this is a constant. And so this brings us to our constant R, which is our ideal gas law constant, or our ideal gas constant, or just gas constant. And incorporating this constant allows us to have an equation where if we know three of our four variables that describe a gas, we can predict the fourth, which is pretty powerful. So let's take a look at that. So here's what we call the ideal gas law. That pressure times volume is equal to the number of moles times the ideal gas law constant, or the gas constant, times temperature. So these are all variables, and this is the equation right here. Puvnert. I mean, if you try to spell it out, it sounds funny. It kind of sticks in your head. That's the way I've always remembered it. Rather than PV equals nRT, it's Puvnert. So our Puvnert, or ideal gas law equation, is one we'll be able to use a lot if we have some information. And that R value, that constant, has a number of different values depending on the units. And so what this R value is really doing, it's allowing us to calculate a variable, and it's basically doing the unit conversion that we need to extract a numerical value for one of our variables that is in meaningful like units. And so that means that our R value is going to have the units of all of those variables incorporated into it. So our pressure units are usually either, atmospheres, or they're going to be something like millimeters of mercury most commonly. These are the common ones we use in chemistry. Our volume is always going to be in liters. Our moles will always have the units of moles. And our temperature will always be in Kelvin, so we have non-zero, so we don't have zero or negative values. And so that means that our ideal gas constant R is that we use with the ideal gas law is going to have units of liters, atmospheres, moles, and Kelvin, or liters, millimeters of mercury, moles, and Kelvin. And so these are the two versions that we're going to use in our ideal gas law equation to make the units work. Now, there's another version of this as well. another set of units that we can convert into, which is joules per moles Kelvin. And this value we're going to use not when we're just calculating the variable properties of gases, but we'll use this one later on. And so this gas constant comes in really handy in a lot of ways. And we'll use it throughout the series. But so for this class, or for right now, for gas laws, we'll most likely use 0.0821 and 62.4 as the variables. And the trick is choosing which numeric value to use, and it will be based on your units. And the difference between these two is in the pressure units. They're totally the same, except for atmospheres or millimeters of mercury. So in the context of the problem, if you are trying to learn or you know the pressure in atmospheres, you'll always use the R value 0.0821. And if you're either trying to find the pressure or you know the pressure in millimeters of mercury, you'll always use the R value 62.4. Let's walk through an example of how to use the ideal gas law. So I'm going to write it up here, Pluvnert. And it's helpful to be comfortable rearranging equations when doing these types of problems. So we have a Goodyear blimp. So the 2017 Goodyear blimp, this is the data I got off 2017. It's really big. So it's the volume of a Goodyear blimp was in 2017 was 8425026. I don't even trust myself to say the number correctly because it's 8,425,026 liters. It's huge. So it's filled with helium gas. Now, what's interesting is for this calculation, the helium piece doesn't matter. All of our gases are the particles are so far apart from each other that the actual mass of it or the size of it doesn't actually matter for the behavior of the gas. And we'll talk a lot about this when we talk about how particles interact in chemistry 162. And gas particles just don't really interact together because they're so far apart. It's really interesting. But it means that we can make predictions based on any type of gas. We'll talk about that more in a bit. So helium gas will be maintained at a maximum pressure of, so we're getting information about pressure, 116 kilopascals. All right, so if the blimp is operating at a temperature, so we're learning about temperature, of 296 Kelvin, how many moles of helium gas are actually contained in this gigantic blimp? So we have 3 known variables and 1 unknown. So what we are trying to solve for here is N. And we know everything else. We know pressure, volume, and temperature, and we always know R. So R is always going to be 0.0821 liters times atmospheres divided by moles Kelvin, or it's going to be 62.4 liters times millimeters of mercury by mole Kelvin. And so that'll be our R value. And we'll choose which one based on the pressure that we're going to do. Our pressure units are in kilopascals, which really aren't atmospheres or millimeters of mercury. So we're going to need to convert into one of these. My personal preference is atmospheres, but I don't know why. You can do millimeters of mercury. You'll get the same answer, just in different units. Either is fine. So we're going to need to convert this value into units of atmospheres if we are going to use this 0.0821 value. So that'll be our first step. And then we'll plug into the ideal gas law. And I'd like to stop for a second and point out a really common misunderstanding when you're first learning about gases. Lots of people see this R value as an equation in itself because it looks like an equation. But this right here is describing the units. Kind of like miles per hour, right? It's miles divided by hours. This is liters times atmospheres divided by moles times Kelvin. It's all one unit. So this is not the same as your ideal gas law equation here. So when you see the actual units, it's not describing the equation. The variables PV, N, R, and T are describing the equation. And if you base this, that volume, that it's R is equal to volume times pressure divided by, the way I see it is usually people say R times pressure times temperature divided by, volume divided by NT, you won't get the correct answer if you're plugging into something like that. Okay, so let's solve this problem. So let's take let's first write down our conversion factor. We know from earlier in these lectures that 1 atmosphere is equal to 101 kilopascals. So we'll use that. So let's start with that conversion. We have 116 kilopascals. I'm going to multiply this. So I have my atmospheres from my conversion factor on the numerator, and in the denominator, kilopascals. So these cancel out. So that 1 atmosphere is going to be equal to 101 kilopascals. So that's going to equal then a pressure of 1.1485 atmospheres. And I'm just kind of keeping all of my units rolling forward. So now we're actually going to plug into the ideal gas law, and we can either plug in our values into PV equals nRT. We can also rearrange it and say that our number of moles is going to be equal to our pressure times volume divided by our gas constant times temperature. And if we put it in the values that the problem gives us here, we should be able to solve this. So our pressure is our converted pressure into atmospheres. So that's our 1.1485 atmospheres times our volume of 425,026 liters, big. That's all going to be divided by this gas constant R. And since we have units of atmospheres, I'm going to use that 0.0821. So 0.0821. And the units are liters times atmospheres divided by moles times Kelvin. And our temperature of 296 Kelvin. So looking at this, I can make sure that my units are going to actually work out. So my atmospheres on top here cancel with the atmospheres in my R value. Same with my liters. And my temperature is on the denominator when you multiply it against the temperature down below. So the kelvins cancel out. So I'm going to have units of moles, which is perfect because that's exactly what I want. So plugging this then just into my calculator, I get a value that is 398,174 moles. That's a lot. If I'm gonna reduce this down to just 3 significant figures to match the sig figs of my pressure and temperature, I would call this 398,000 moles. So that's how we use our ideal gas law.